Today I'm excited to present our work on QiMeng-Xpiler, a system for transcompiling tensor programs across deep learning systems using a neural-symbolic approach. This project is a collaboration between researchers from these organizations. Because of the visa problem, the author cannot attend the conference in person. So I will be delivering this presentation on his behalf. In recent years, deep learning has grown very fast. At the same time, many different types of hardware have appeared, like GPUs, CPUs with vector instructions, and special chips like NPUs. To get good performance on each device, developers often have to write different low-level versions of the same program for each platform. This process takes a lot of time and effort. It also makes the code hard to reuse and slows down the new development. Each of these deep learning systems comes with its own unique programming interface. CUDA for NVIDIA GPUs, HEAP for AMD GPUs, ANC for Cambricon NPUs, and vector intrinsics like VNI for Intel CPUs. Just showing in this table, the characteristics fall into three categories: parallelism, memory hierarchy, and specialized intrinsics. Let me briefly explain three common ways to generate operators. The first is rule-based. Experts write rules by hand to transform code. This gives high accuracy, but it takes a lot of time and deep knowledge. The second one is data-driven. Neural networks learn to generate code directly. It's fully automatic, but often not accurate, especially when the code must follow the hardware rules. The third one is symbolic synthesis. This method trying to create correct code using examples or DSLs. They use tools like SMT solvers to search possible solutions. They can be accurate but don't scale well and still need some manual setup. We compare these three methods in a diagram showing that the trade-offs between accuracy, automation, and scalability. Now let me introduce our approach, the QiMeng Transcompiler. Unlike previous methods that rely on manual rules or end-to-end learning, we take a neural-symbolic approach by combining LLM with SMT-based symbolic reasoning. The key of QiMeng-Xpiler is that programming translation is automatically conducted as a series of LLM-assisted transformation passes, where incorrect code snippets are repaired by small-scale symbolic synthesis, and the optimal transformation passes are identified via hierarchical auto-tuning. To automatically convert tensor program between different deep learning systems, our transcompiler consists of two key components, as illustrated in this figure. The first one is neural and symbolic code conversion. We first use LLM to do the initial code translation. Then to fix any possible errors, we use an SMT solvers to correct small mistakes. This way, the translation is both flexible and correct. The second one is hierarchical performance auto-tuning. To generate performance code, we adopt a hierarchical tuning framework and systematically explore both the order of transformation passes and their parameter settings. At the interpass level, we use MCTS to explore different combinations of transformation passes. At the interpass level, we introduce a constraint-based auto-tuning mechanism to optimize low-level parameters such as tile size and the loop alters. To make code translation automatically and fast, QiMeng-Xpiler uses a hierarchical tuning methods. It first explores high-level strategies like how to parallelize and assign threads, then tunes low-level details like tile size and loop alters. By separating these two parts, QiMeng-Xpiler can find the best performing translated code more easily. And we evaluate QiMeng-Xpiler on 168 test cases for each transcompiling direction across 4 deep learning systems with distinct programming models. And we evaluate QiMeng-Xpiler along 3 key dimensions. The first is compiling accuracy. Then the next is computation accuracy. And the third one is execution performance. And in this table, QiMeng-Compiler performs better than the SODA rule-based. These results show that QiMeng-Xpiler's flexibility across various DLS, while rule-based methods cannot. We conduct an ablation study to further analyze our methods as shown in the table. QiMeng-Xpiler can translate programs across different processors and programming models. For example, SIMT or SIMD. The real-world C or CUDA to ban a program translation with a functional correctness rate is 91.7%. And we evaluate the performance on the 4 most common program transcompilation directions as shown in the figure. Results show that QiMeng-Xpiler achieves an average performance of 0.78 times than its manually optimized counterparts across the 4 transcompilation directions and various operators. Performance can reach up to 2 times that of manually optimized vendor-provided code. Meanwhile, we evaluate how QiMeng-Xpiler's performance varies across different source platforms when targeting the same target platform. The figure shows that the normalized performance of 3 representative operators. Results show that the transcompiled programs achieve comparable performance. To evaluate QiMeng-Xpiler's effectiveness on real-world kernels, we conduct a case study on FA1 and FA2. This table shows that the performance of QiMeng-Xpiler on FA1 and FA2 compared to vendor-optimized implementations on different transcompilation directions. Results show that QiMeng-Xpiler achieves 0.61 times to 0.81 times the performance of its native implementations on all transcompilation directions. And we further evaluate how QiMeng-Xpiler improves programming productivity in real-world scenarios. Specifically, we compared the development cost on deformable attention with around 200 logs. A table shows that programming productivity is improved by 34.3 times for GPU and 96 times for MLU, where transcompiling latency tensor program. In conclusion, we propose QiMeng-Xpiler, a system that can automatically translate tensor programs across different platforms using a neural-symbolic approach. It uses LLM to guide code transformation and fixes any errors using symbolic synthesis. In our experiment on 4 deep learning systems, QiMeng-Xpiler translates codes correctly with 95% accuracy on average and runs at 78% the speed of manually optimized libraries, and improves development efficiency by up to 96 times. Thank you for your attention, and if you have any questions, please feel free to reach out to the author via email. Thank you.